All right, this video is going to go over the bonding review. Just a couple of things about the test. The first thing is we are going to have 20 multiple choice questions that definitely have vocab. I strongly encourage you to know 1 through 15 for vocab purposes. And then there's 2 short answers and 9 drawings. You definitely want to know about sigma and pi bonds, bond strength versus bond length, okay? So the first one, single covalent bond is 2 shared electrons, 1 pair. Here's an example. Remember, carbon likes to have 4 bonds. A double covalent bond is 4 shared electrons, 2 pairs shared between 2 atoms. It doesn't matter what structure you have. Obviously, it should show, though, that they have single bonds, double bond here. Triple bond, triple covalent bond, 6 shared electrons shared between 2 atoms. Coordinate covalent bond is the idea that a bond in which one atom contributes both bonding electrons. In this case, oxygen has more. It's contributing to its coordinate covalent bond. Resonance is one of the 2 or more equally valid electron dot structures of a molecule or polyatomic ion. So then here, remember, resonance, you're going to put a double-sided arrow between resonance structures. Polar molecule, an unequal distribution of electrons. You should have a dipole pointing towards the O, and another one here, so the overall direction's up. A nonpolar molecule is an equal distribution of the electrons. In this case, we have a dipole pointing towards the right, one towards the left, and they're going to cancel. Pi bond is a bond formed above and below the bond axes of the bonded atoms. Sigma bond is a bond formed when 2 atomic orbitals overlap on the bonding axes. Okay? VSEPR is the idea that valence shell electron pair repulsion theory predicts the 3-dimensional shape of molecules based on the fact that molecules adjust their shape to keep pairs of electrons as far apart as possible. Remember, lone pairs need more space. Now we have our 3 intermolecular forces. Dispersion, weakest of the 3 intermolecular forces, weak attraction between nonpolar molecules caused by movement of the electrons. Dipole-dipole, it happens when we have polar molecules. Hydrogen bonding is the strongest. I would know that hydrogen bonding is the strongest. Hydrogen bonding is when you have HF, HO, HN connected, and they are the strongest because they have a high difference between electronegativities. Now we're on the second page. Bond dissociation energy is the energy required to break a bond between 2 covalently bonded atoms. Bond length, distance between 2 bonding nuclei. Remember, the single bond, right, is going to be the longest, then double, then triple. When it comes to bond dissociation energy, the triple is the strongest, then the double, and then the single. So bond strength is inversely proportional to bond length. Strength, triple bond, is greater than double, single. Like dissolves like. Polar molecules dissolve in polar solvents. Nonpolar dissolves in nonpolar solvents. So remember things like nonpolar solutes, iodine, CO2 are nonpolar. They would dissolve in oil, which is also nonpolar. 18, you have to know this table, right? When it comes to sigma bonds, each type of bond has 1, and then pi bonds don't start until double and triple. So single bond has 0 pi, double for 1, triple has 2. Here, right, we have C2H4, number of sigma bonds 5, pi bonds 1. C2H6, which is the structure that you saw in the lab, and this one, right, we have 12 sigma, 3 pi bonds. And then this one here, we have C4H6, 9 sigma, 2 pi. All right, now we're looking at the structures. On the test, you're going to, once again, have the 20 multiple choice, 2 short answer, 9 drawings, and then those drawings are going to take up 1 page front and back. So if you could do the review, right, in 50 minutes or a little bit more than 50 minutes, you should be okay with time. Let's look at these structures, though. This is N2, no resonance. It is linear, so you should draw it straight across. Nonpolar covalent, nonpolar dispersion. NO3, 1 minus, right? has 3 structures, brackets in charge for a polyatomic, double-sided arrows to separate the resonance structures, trigonal planar, polar covalent, non-polar covalent for the molecule type, dispersion for intermolecular forces. SiCl4 can be drawn like a plus sign. Don't forget to have your number of lone pairs on each of your oxygen. So like when it's double bonded to an O, these should have 2 lone pairs. Single bonded should have 3 lone pairs. Here, SiCl4 should have 3 lone pairs on each Cl. No resonance. It's tetrahedral, polar covalent. Dipoles cancel, so it's nonpolar. You end up with dispersion, intermolecular forces. When it comes to H2O, that's water, right? No resonance. It's bent. It should look bent. You're going to have dipoles because we know water is polar. You're going to end up with polar covalent. Dipoles do not cancel, so polar, and it's hydrogen bonding because you have H directly attached to O. Bi3 here, no resonance. Remember, careful with the B's. So this is an exception. Trigonal planar. Notice how the dipoles are equal angular, right? Same amount of force. So we have dipoles, polar covalent, but they cancel because they're equal angular, so it's nonpolar, and dispersion. Next one is SF6. You can draw it like this, right, or like this, but you're going to show that it has no resonance. It's octahedral, polar covalent. Dipoles cancel because they're equal angular on the planar part, and then also these two cancel, right? So nonpolar and dispersion. Now we're moving on to the last page. We constitute this as C1, C2, C3. You technically could have these flipped, so then you would just look at your answers based on this, right? So if I say that this is C1, this is C2, this is C3, this carbon has 4 things attached, tetrahedral. This carbon here has 1, 2, 3 things attached, trigonal planar. This one here has 3 things attached, trigonal planar. So if you have like the flip of this one, right, and you have the double bond here, then your answers would be trigonal planar, and then the last one would be tetrahedral. Nonpolar covalent, so it's nonpolar molecule dispersion for intermolecular forces. O3, you have bent structure. You're going to have resonance because you have a single and a double, and all things attached are the same. Don't forget your lone pairs on the central atom. You're going to have a double-sided arrow to separate the resonance structures. Yes, there's resonance. Nonpolar covalent, because there's no dipole. It's automatically nonpolar. Dispersion. This one here we drew in the lab. No resonance, trigonal planar, nonpolar covalent, polar covalent. The dipole doesn't cancel, so it's polar. Dipole. BeH2, careful with the B's, another exception. No resonance, linear, polar covalent. The dipoles cancel, nonpolar dispersion. H3O plus, brackets in charge, arrows all pointing up. No resonance, trigonal pyramidal because you have the lone pair. Polar covalent, it is polar because it has an overall direction up, and it has hydrogen bonding because it's H connected to O. PCl3 here has no resonance. It's trigonal pyramidal because you have the lone pair on top here. Polar covalent, all the dipoles point towards the Cl. The molecule is polar because it has an overall direction down, and it is dipole-dipole. So that concludes the review. Make sure that you know the names of the shapes for the test, right? You have to know what values constitute polar covalent, nonpolar covalent, and you should know what type of intermolecular forces there are and what makes it hydrogen bonding, dispersion, or dipole-dipole.